Alright, so this is the final video in this little series here where we're going to be going over the AP Calculus mini exam that I've written. So we've already gone through the first 3 parts of this 4-part exam. We've gone through both the multiple choice no calculator and calculator, and we've gone through the free response calculator. So now we're going to finish off with the free response no calculator section. Alright, section 2 part B. We're going to have 30 minutes for 2 problems. So it's again 15 minutes per problem, just like in the first section, in the first part of this section, okay? But in this time, there's no calculator allowed for these problems, okay? So anything that you'll need to do will be easily done by hand, okay? So without further ado, let's begin and look at question 2 of the free response, okay? So we have the Upper Hills Pencil Sharpening Factory contains 2 branches, branch A and branch B. The rate at which pencils are sharpened at the 2 factories is given by strictly increasing twice differentiable functions a of t and b of t respectively, where they're both measured in thousands of pencils per hour and t is measured in hours, between 0 and 9. Selected values of b of t are shown in the table to the right. Additionally, it is known that a of 0 equals 1 and a double prime of t is greater than or equal to b prime of t for 0 is less than or equal to t is less than or equal to 9. In part A, we're asked to approximate b prime of 5 and explain what it means in the context of this problem using correct units. Alright, so to approximate b prime of 5, we're just going to go here and find 2 points that are close to 5. So in this case, we got 3 and 7, and we're just going to find the slope between those 2 points, right? So b prime of 5 is approximately equal to b of 7 minus b of 3 over 7 minus 3. This is the y2 minus y1 over x2 minus x1 thing. And so b of 7 is 6, b of 3 is 4, and 7 minus 3 is 4. 6 minus 4 is 2 over 4, which is 1/2. Okay, now I need to explain what this means in the context of this problem using the correct units, right? So b of 5 tells us the rate at which pencils are being sharpened at the factory, right? So b prime of 5 tells us how quickly that's changing at time t equals 5. So I'm not going to write it out for the sake of time, but actually, you know what? No, this isn't an AP video. I can write it out. This video isn't going to be an hour long, so we can write it out. So at t equals 5, the rate at which the number of pencils are being sharpened. So the rate at which the number of pencils are being sharpened, that's b of t, right? The rate at which number of pencils are being sharpened. Right, this is b of t, the rate at which the number of pencils are being sharpened, that's b of t, right, the rate at which pencils are being sharpened. And this is changing at a rate of 1/2, right? So it is changing, because that's what b prime of t is telling us. It's telling us how quickly b of t is changing. So it's changing at a rate of, should have given myself a bit more space, I guess. It's changing at a rate of 1/2, and now for the units, we have, so b of t is measured in thousands of pencils per hour, right? And you can see here, when we find the derivative, we're basically taking b of t and dividing it by t, right? Because we have t on the bottom, hours on the bottom. So when we're looking at the units, it's going to be the units for b of t divided by the units for t. So b of t is in thousands of pencils per hour, and t is in hours. So the units for b prime of t are going to be thousands of pencils per hour per hour. So I have to zoom in a bit here to write. It's going to be thousands of pencils per hour. So it's double per hour squared. Okay, that is part A. Now we can look at part B. So part B says, a student correctly uses the midpoint sum to approximate that the definite integral from 0 to 4 of a prime of t dt equals 4. Explain what this means in the context of this problem and determine whether the student's approximation is an underestimate or an overestimate. Okay, so first of all, let's think about what this is, alright? So we see the integral from 0 to 4 of a prime of t dt. And we think about, okay, so if I'm integrating the derivative, these just kind of cancel out. I'm just going to get a of 4 minus a of 0, right? Well, what is this? This is just delta a, right? It's a change in a from 0 to 4, right? So this integral is telling us how much a changed between 0 and 4. So what this is telling me is, since I know this is equal to 4, this means that the rate at which pencils, I apologize for my handwriting here, it's not the best, were being sharpened at factory A. Okay, and I also want to be specific, and I also mentioned the time. So between t equals 0 and t equals 4. So you want to be pretty specific between t equals 0 and t equals 4. You want to be pretty specific when you're answering these kind of things. And t equals 4 changed by 4, and then now for we're just using the units for A again, right? Because telling us how much A changed, so just give me the units for A. 4,000 pencils per hour. Okay, and that is the first part. Now I really should have given myself a bit more space. The large writing is kind of messing with me here. And now we need to determine whether it's an underestimate or an overestimate. Okay, so we're using a midpoint sum, right? We're using a midpoint sum. And so I need to determine, is this midpoint sum an underestimate or an overestimate, right? And whenever I'm looking at midpoint sums, I'm looking at the second derivative, I'm looking at the concavity, right? So we're looking at f prime of x, and in this case it's going to be a double prime of t, right? So a double prime of t is what we're looking at. Okay, so we need to look at, is a double prime of t positive or negative, right? That'll tell us the midpoint sum, is it an underestimate or an overestimate, right? And so we should look up here, and we have to kind of follow a little roundabout path. So we know that a double prime of t is greater than b prime of t, right? We're also given that b is a strictly increasing function, okay? So what this means is that b of t is increasing, right? What that's telling me is that b prime of t is greater than 0. It has a positive slope. That means that's why it's increasing. But we also know that b prime of t is less than or equal to a double prime of t, right? A double prime of t is greater than b prime of t. So since b prime of t is greater than 0, this must mean that a double prime of t is also greater than 0, right? So we know that a double prime of t is greater than 0, and so we were looking at a double prime of t, and now we know that it is greater than 0. It's positive, right? So because, I'll do that here, because a double prime of t is greater than 0, a is concave up, and so the approximation is an underestimate. Right? That's something you should know. Or if it's a midpoint sum and it's a concave up function, then it's an underestimate. Underestimate. There we go. Okay. And that is part B. Now let's look at part. That was all right. Yeah, explain, determine what's an underestimate or underestimate. We said underestimate. Here's our answer. Okay. Now part C. At time t equals 4, it is found that the two factories are sharpening pencils at the same rate. Is b of 4 greater than, less than, or equal to 5? Justify. Okay. So we know that the two factories are sharpening pencils at the same rate, right? So at time t equals 4, the rate at which A is sharpening pencils is given by a of 4, and the rate at which factory B is sharpening pencils is given by b of 4. So since they're sharpening at the same rate, you can say that a of 4 is equal to b of 4, right? So now, since we have this integral here, we can use this integral to help us figure out what a of 4 is. Okay, all these will give us more information about a of 4, right? So we said that this thing was equal to a of 4 minus a of 0, right? This integral is equal to a of 4 minus a of 0. And we know that it's an underestimate, right? So the actual value, so if the approximation says it's equal to 4, but it's an underestimate, the actual value must be more than 4, right? Maybe it's 4.1 or 4.2 or something, but this is an underestimate, so it only said 4. So the actual value is actually greater than whatever the estimation said. So we know that a of 4 minus a of 0 is actually greater than 4. However, and not however, but like also, we know that a of 0 equals 1, right? So a of 4 minus 1 is greater than 4. So now I can find a of 4, and I'll say a of 4, I don't know what it exactly is, but I know that it's greater than 5, right? 4 plus 1 is 5. So since I know that a of 4 is equal to b of 4, this tells me that b of 4 is also greater than 5. So is b of 4 greater than, less than, or equal to 5? Justify. So it is. So b of 4, we'll say it's greater than 5 because a of 4, which is equal to b of 4, is greater than 5. Okay? Yeah, so b of 4 is greater than 5. Alright. Now part D. Upper Hills decides to expand and purchase a new branch, branch C, which sharpens pencils at a rate of C of t is equal to the absolute value of t minus 1 plus 2, where t is between 0 and 9. Can it be concluded that there is at least one time t, where t is between 0 and 9, where c prime of t equals 7 over 9? Explain. Okay, so this is a mean value theorem question, right? Where you're finding a time t is in between two other times where the derivative is equal to the average value, okay? So the mean value theorem is just a quick recap. The mean value theorem says that the average rate of change across a of b, a comma b, right, is equal to f prime of c, where a is less than c is less than b. So there's some number c that's in the middle of a and b, so it's in between, it's in this interval, where the derivative is equal to that average rate of change, okay? Now there are some conditions though, right? This only works if the function is differentiable across the entire interval. So they must be differentiable. Now you'll notice something interesting about this function. It's an absolute value function. It's the absolute value of t minus 1 plus 2. So at t equals 1, right, it looks like this sharp point here. So this actually is not differentiable at t equals 1. The c function is not differentiable there. So we can say that since c prime of t does not exist at t equals 1, the mean value theorem doesn't even apply. So we can just ignore all of this because c prime of t isn't even defined at t equals 1, so it doesn't even meet the conditions to state this. So c prime of t is not defined at t equals 1, so the mean value theorem does not apply, and no such conclusions can be made. Okay, so they're saying, can it be concluded that there's at least one time t where the derivative is equal to this value? We're saying no, because no such conclusion can be made. You'll notice though, if you actually do calculate the average rate of change across 0 and 9, you do get 7 over 9, because that's going to be c of 9 minus c of 0 over 9 minus 0. C of 9 is 9 minus 1 is 8, plus 2 is 10, minus c of 0 is going to be 0 minus 1 is negative 1. Absolute value of that is 1. 1 plus 2 is 3 over 9, which is 7 over 9. But because it's not defined at, the derivative is not defined at t equals 1, this is never, we cannot say for sure that it's equal to the average, or it's equal to the derivative at some point. Okay? And you'll actually notice that if you were to graph it, since it would look like this curve, there's only two different derivatives. It doesn't like continuously change. So actually, in fact, there is no point where it's equal to this. Okay? So yeah, this is our answer. There's no such conclusion that can be made. And that was part D, and that ends question 1, right? So let's look at question 2, right? Because question 1 was this guy from the calculator section. So this is question 1, question 2. Now we're on question 3. Consider the differential equation dy dx equals 2y tangent of x secant squared of x. Let y equals f of x be the particular solution to the differential equation that passes through the point 0, e squared. In part A, we're asked to write an equation for the line tangent to the graph of f at the point 0, e squared. Okay, so whenever you see this thing where they ask you to want you to write an equation for the tangent line, you always write down two words: point and slope. Okay, so the point is going to be 0, e squared. Right there, nice enough to just give it to us straight up. And then the slope is going to be the derivative evaluated at that point. So in this case, evaluated at 0, e squared. And so if we plug in 0 and e squared in for y and x here, we'll get that derivative. So it's going to be 2 times e squared times tangent of 0 times secant squared of 0. Right, now it's going to be 2 times e squared, tangent of 0 is 0, and secant squared of 0 is 1. But since there's a 0 here, this whole thing is just equal to 0. So when we go ahead and write our equation for the tangent line, we'll get y minus e squared equals m, which is 0, times x minus 0. So this whole thing just goes away, and we just get y equals e squared as our tangent line equation. Okay? Now in part B, we need to find y equals f of x, which is the particular solution to the differential equation that passes through 0, e squared. So the first thing that we're going to do here is we're going to separate our variables, so bring all the y's onto one side and all the x's onto the other side. If we do that, we'll take this y, bring it over, we'll get 1 over y dy equals 2 tangent of x secant squared of x dx. Now this 2, you could bring it over there, it's not going to really change the answer, but as you can see here, this 2 is going to make this calculation a bit more clean. Not really that big of a deal, okay? So now since we have this, we're to go ahead and integrate both sides. That's the next step. If you remember, the integral of 1 over y, that's defined as the natural log of y. Okay? And then for this one, we're just going to do a u substitution here, because I know that the derivative of secant is secant tangent, right? Well, this is just equal to 2 tangent of x, secant of x, secant of x, right? So I have my secant, this is my function, and I have my derivative of that function here, right? This is secant of x, this is the derivative, which is secant tangent, right? So I'm going to do a u substitution where u is equal to secant of x. U equals secant of x, so then du dx equals secant of x, tangent of x, and then du is equal to secant of x, tangent of x, dx. I'd bring that dx over here, and then I'll substitute this in for here, and I'll get the integral of 2u du, right? So the u is secant of x, and then the remainder, the secant of x, tangent of x dx, that's the du. Okay? So now I have the integral of 2u du, which is just u squared plus c, right? It'll be u squared over 2, but then this 2 and this 2 cancel, and we're just left with u squared. And remember, u is equal to secant of x. This is equal to secant squared of x plus c. So we have ln of y equals secant squared x plus c. And now we have to solve this for y, okay? So what I'm going to do now is I'm going to pick e here as the base for both of these. And I'm going to get y equals e to the secant squared x plus c. And now I can split this up, and I'm going to say, since I'm adding two things here in the exponent, I can say this is e to the secant squared of x times e to the c. And e to the c, this is just a constant, right? It's a constant to a constant. So I just get y equals c e to the secant squared of x. Now, I'm going to plug in my initial condition, which is 0, e squared, right? If I plug that into here, I'll get e squared equals c times e to the secant squared of 0. Well, remember, secant is 1 over cosine. So cosine of 0 is 1. This would be 1 over 1 squared, which is just 1. So I get that e squared equals c times e. And then if I solve this for c, I get c equals e. So if I put that back in my original equation, I'll get y equals e times e secant squared of x. And to be honest with you, this double e kind of looks a little bit weird. So I actually personally prefer the version where it's e secant squared x plus 1. This step might have been a little bit unnecessary, but this is also obviously, these are both the same thing, but I just like the way this one looks a bit better, so I'm going to stick with that as my final answer. Okay, that's part B. That's all they wanted, right? They wanted y equals f of x. Now in part C, we have something interesting here. Let g of x equals f of x minus e squared and let h of x equals this piecewise function, where it's x, where x is less than 0, and it's x plus 1, where x is greater than or equal to 0. And I want you to find the limit as x approaches 0 of this composite thing, g of x times, not composite, but like this combination g of x times h of x, or show that it does not exist. Okay? Now, I feel like a lot of people would immediately see this piecewise function and say, oh, it's approaching 0 from one side, and it's approaching 1 from the other side. So obviously, this composite function, I can immediately say it does not exist, because h of x, the limit is x approaches 0 of h of x is not defined. That is true, but you can't just immediately take that jump in logic. You have to show that by taking the limit from the left and the limit from the right, okay, of this composite function. This function here, g of x, h of x, okay? And so we know what f of x is, right? This is f of x. So we can go ahead and find g of x now. G of x equals f of x minus e squared. So it's equal to e to the secant squared of x plus 1 minus e squared, right? And now we want to find this limit, and we're going to approach it from the left and from the right. So if it approaches the same number from the left and from the right, then it does exist. If not, then it doesn't exist, okay? So we'll take the limit. We'll start with the left. X approaches 0 from the left of g of x, h of x, right? And so I can split this up, and I can say, okay, it's the limit as x approaches 0 from the left of g of x times the limit as x approaches 0 from the left of h of x, okay? And so this guy, as x approaches 0, secant of x approaches 1, right? Because the graph of secant of x is like around x equals 0, it's like this. It's approaching 1, okay? Erase. Okay, so it's equal to 1. So e to the, so g of 1, so g of 0 is equal to e to the secant squared of 0 plus 1 minus e squared. Secant of 0 is 1, so secant squared of 0 is also 1. So it's e to the 1 plus 1 minus e squared, which is e squared minus e squared, which is 0. Okay, so this guy here is equal to 0. And then this guy, as x approaches 0 from the left of h of x, that's going to be this part of the function, because we're coming from the left, right? So it's equal to 0. So this part is equal to 0 times 0, which is 0, right? Now I can do the same thing from the right. G of x, h of x is going to equal the limit from the right of g of x times the limit as x approaches 0 from the right of h of x, and just like last time, this guy is going to equal 0, right? Because it's still approaching 0. It's still approaching. This guy's still approaching 1, so it's still going to be e squared minus e squared, so it's still going to be 0. And then from the right, for h of x, we see it's approaching 1 here, because 0 plus 1 is 1. But notice that it didn't really matter what this guy was approaching, because this was 0. So it still equals 0. So what we have now is we have that this limit from the left is approaching 0, and from the right it's also approaching 0. So the limit as x approaches 0 from the left of this function is equal to the limit as it approaches 0 from the right, right? They're both equal to 0. So what I can say is that the limit as it approaches 0, just in general, equals 0, because the limit from the left equals the limit from the right, okay? And there is the final answer, and that is the end of this exam, right? End of section 2 part B, and now we just have the solutions for the entire thing, right? So that was that was 2 questions, 2 response questions. I hope you found those helpful, and then yeah, just do a lot of practice, get ready for the AP exam. Good luck everyone, and like and subscribe, and I'll see you in the next video. Goodbye.